Okay, let's continue on chapter 7. We're going to talk about the L'Hopital rule today. And L'Hopital rule is mainly used for to find out the limit for the indeterminate form. Okay, so indeterminate form and the L'Hopital rule, that's the main focus for this particular section. So we're going to learn how to recognize limits that produce indeterminate forms. Then we'll learn how to apply the L'Hopital rule to evaluate a limit. So first of all, let's take a look at the indeterminate form. So a typical indeterminate form is either 0 over 0 or infinity over infinity. Right? So two typical indeterminate form, meaning you do not know the result for these two particular forms. Okay, as I mentioned, 0 over 0 and then infinity over infinity are called indeterminate state or indeterminate form because they do not guarantee the limit exists. And they do not tell you what the limit is if the limit exists. So when you encounter one of these indeterminate forms earlier, we learned some techniques. You can use some algebraic technique to find out a limit. For example, right? Let's take a look at this limit. Limit when x approaches -1 for the function 2x squared minus 2 over x plus 1. So here, in this particular, you apply the algebraic. So you factor out 2, you get x squared minus 1 over x plus 1. Now you factor x squared minus 1, so you end up with x plus 1 is the difference of two squares. Now you cancel x plus 1. That's why you end up with this limit where x approaches -1 and 2 times parentheses x minus 1. And now what you need to do is replace. You can do direct substitution, replace x with -1. Now you end up with -1 minus 1 becomes -2. -2 times 2 making -4. So that's why this limit equal to -4. So the algebraic expression technique we use is divide both numerator and denominator by x plus 1. And we can also, this is a typical 0 over 0 indeterminate form. If you look at it, we plug in -1. So you get a 2 times -1 squared minus 2 over -1 minus 1 plus 1. Numerator becomes 0, denominator becomes 0, so this is a typical 0 over 0 indeterminate form. If you take a look at the second one, okay, limit when x approaches infinity for function 3x squared minus 1 parenthesis over 2x squared plus 1 parenthesis. So again, if you plug in infinity, so you get 3 times infinity squared minus 1 over 2 times infinity squared minus plus 1. And all this constant compared to infinity is insignificant. So this is basically becomes infinity over infinity. That's why it's infinity over infinity. So here, what you need to do is divide every single term by x squared. Every single term on numerator and denominator by x squared. So you get 3 minus 1 over x squared over 2 plus 1 over x squared. And you plug in infinity here, 1 over infinity squared becomes 0. So this term basically is 0. 1 over infinity squared is 0. Okay, so it's 3 over, so it becomes 3 over 2. So that's going to be the limit. So the algebraic technique we use here is divide every single term in the numerator and denominator by x squared. All right. let's take a look at this one. Limit when x approaches 0 for e to the 2x minus 1 over e to the x minus 1. If you do direct substitution, you're going to get e to 2 times 0 minus 1 over e to the 0 minus 1. So it becomes limit x approaches 0 is e to the 0 minus 1 over e to the 0 minus 1. E to the 0 is 1, 1 minus 1 over 1 minus 1. So again, this is 0 over 0 indeterminate form. So now again, you factor the numerator, right? This is difference of two squares. So e to the x plus 1 parentheses times e to the x minus 1 parentheses. We're going to cancel e to the x minus 1. So end up with the limit when x approaches 0 for e to the x plus 1. Now you're going to replace x with 1. Do direct substitution, you get e to the 0 plus 1. E to the 0 is 1. 1 plus 1 give you 2. Okay. So again, a lot of indeterminate form, you could just apply the algebraic technique to solve it. And however, now let's take a look at this particular example. Limit when x approaches 0 for e to the 2x minus 1 over x. So again, if you do direct substitution, so you get e to the 2 times 0 minus 1 over 0. So denominator definitely is 0. Numerator e to the 0 minus 1 is also 0. So again, you produce 0 over 0 indeterminate form. And again, here it's not easy to apply it's impossible basically to apply the algebraic skills to get to the final result for a limit. So think of this as another type of questions. You have to apply some other method in order to get to the final result. And when we talk about a limit at the very beginning, we could create a table, right, to estimate the limit. So basically, let's take a look at this. So when you graph it, okay, this is actually the graph, and look like when x approaches 0 from the left and then x approaches 0 from the right, give you the limit of 2. If you look at the table, right, pick some values from the left hand side of the 0 and then some values from the right hand side of the 0. And you also see the pattern. From the left hand side, the numbers get closer to 2. From the right hand side, the number get closest to 2. So yeah, as you can see, you probably will figure out that the limit when x approaches 0 is equal to 2. So now let's get to the L'Hopital rule, which used to find a limit for indeterminate form when the algebraic scales fails. Our algebraic technique does not work. And you cannot apply the algebraic technique to solve the problem. Okay, so that's where the L'Hopital rule was first invented and then applied to solve the problem. Okay. So let's take a look at this. Find a limit illustrated from the previous example. We're going to use the L'Hopital rule. It's named after a French mathematician L'Hopital. This theorem states that under certain conditions, the limit of the quotient f of x over g of x is determined by the limit of the quotient of the derivatives f prime of x over g prime of x. So the key thing is applying the derivative to find a limit, okay, on both numerator and denominator. So let's take a look at L'Hopital result. Let f of x and g of x be functions that are differentiable on the open interval a comma b containing c, except possibly at c itself, assuming that g prime of x is not equal to 0. Okay, that will make the quotient for the derivative defined for all x in a comma b, except possibly at c itself. The limit of f of x over g of x as x approaches c produces the indeterminate form 0 over 0. Then limit for x approaches c for f of x over g of x equals limit x approaches c for f prime of x over g prime of x. It could be the indeterminate form is not limited to 0 over 0. It could be infinity over infinity. Okay, either form will be good. And provided limit on the right exists, this result also applies if the limit of f of x over g of x as x approaches c produce any one of the indeterminate form. Basically infinity over infinity, negative infinity over infinity, infinity over negative infinity, or negative infinity over negative infinity. So infinity over infinity has 4 different forms. Right? Both positive, numerator negative, denominator negative, and both negative. Okay, so 4 different forms. So this is basically the L'Hopital rule. Find the derivative of numerator, find the derivative of denominator, find the quotient. The quotient is the limit, and plug in c, right, at the end. Alright, now let's take a look at this question. Applying the L'Hopital rule, we know that this is 0 over 0 indeterminate form, right? We already go over that. So that means we need to take in order to find the limit, we need to take the derivative of the numerator. So derivative of e to the 2x, you're going to use the chain rule. So it's e to the 2x, setting u equal to 2x. So it's u times u prime. So it's u times u prime. U is e to the 2x times u prime. Derivative of 2x u prime will be just 2. Okay, so times 2. So the answer is 2 times e to the 2x. And derivative of constant negative 1 is 0, right? Intermediate derivative of x is just 1. Right now, denominator is not 0 anymore. So you can do direct substitution, replace x with the 0. So limit 2 times e to the 2 times 0 over 1. E to the 0 is 1, so it becomes limit 2 times 1 over 2. So, no, 2 times 1 over 1. So that becomes 2 over 1. 2 over 1 is 2. As you can see, this actually matches with our analysis based on the graph and also the table. Okay, in the background, just detailed solutions. You can take a look at it. And the form 0 over 0, infinity over infinity, infinity minus infinity, 0 times infinity, 0 raised to 0 power, 1 raised to infinity power, and infinity raised to 0 power has been identified as indeterminate. And there are similar forms you should recognize as determinate, meaning infinity plus infinity is infinity. Minus infinity is negative infinity. 0 raised to infinity power is 0. And 0 raised to negative infinity power is infinity. you can also view it as 1 over 0 to infinity. Since 0 to infinity is 0, 1 over 0, that gives you infinity. So remember that L'Hopital rule could be applied only to the quotient leading to the indeterminate form of 0 over 0 or infinity over infinity. Nothing else, like just these two forms. Let's take a look at this. Okay, for instance, the following application of the L'Hopital rule is incorrect. Why is that? Because it's not 0 over 0 or infinity over infinity. If you do direct substitution, limit when x approaches 0 is e to the 0 over 0. E to the 0 is 1. 1 over 0. This is not indeterminate form. So that's why L'Hopital rule is not applied here. Okay. So basically, just be careful when you try to use the L'Hopital rule. Always double check or make sure it's indeterminate from 0 over 0 or infinity over infinity. All right, let's just take a look at one more question. I'm going to wrap up this particular section. All right, let's take a look at this. So if you do direct substitution here, evaluate the limit using L'Hopital rule. I mean, it's obvious we're going to use L'Hopital rule, but you need to always double check, make sure it's either 0 over 0 or infinity over infinity. Okay, let's see. So we're going to do direct substitution. Replace x with a 0, so e to the 0 plus 2 times 0 minus 1 over 6, 0. E to the 0 is 1, so numerator is 1 plus 0 minus 1, denominator is 0. So 0 over 0. So definitely L'Hopital rule applies, right? L'Hopital rule applies here. So all you need to do is find the derivative of the numerator. So derivative of e to the x is e to the x. Derivative of 2x is just 2. Derivative of negative 1 is 0. Derivative of 6x is 6. Okay. Now you do direct substitution. Replace x with 0. So e to the 0 plus 2 over 6. So e to the 0 is 1, as I mentioned many times. So it becomes so it just becomes 3 over 6. 3 over 6 is half. Okay, so the answer for this limit when x equals 0 for this particular function, e to x plus 2x minus 1 over 6x equal to half. And that is pretty much it.